Okay, so this is Tuesday, and for some reason I pushed the record button today, but it didn't record. It hung up. So since I want to use this for an online class, I'm going to go ahead and record it. Anyway, so what we were on was section 5, and talking about integration by partial fractions. So the idea is to take a rational expression with a denominator that you can factor and to come up with the two fractions that are equivalent to the original fraction. So if you remember last class, we had this 1 over x squared minus 1, and you can factor the denominator to x minus 1 times x plus 1. So these are what we call two distinct linear factors. We want to take this, which we do not know how to integrate. We could actually integrate it using trig substitution, but what we'll find out is that there are usually sometimes two or more ways to solve a problem. So this is solving it using partial fractions. So what we're going to do is we're going to break it up into two fractions. A divided by x minus 1, which is the first factor, and b divided by x plus 1. So what we did, remember, is we chose x. What we did is we combined these two into a single fraction with the same denominator. Then we set the numerators equal to each other. And then we chose x to be either x equals 1 or negative 1, such that this term goes to 0 or this term goes to 0. And we solve for a and b. And so our original fraction could be written as two fractions, each simpler, just a single factor. And then when you integrate that, so integrating the original rational expressions is the same as integrating the two separate parts of the partial fraction. And when you have dx over x plus or minus something, it's always going to be just the natural log of the absolute value of x plus or minus something. In this case, it was plus or minus 1. You've got this factor of a half. So those were distinct linear factors. And we'll look at another one later in the class. So the second case is what we call repeat linear factors. So our example is going to be 2x minus 3 over x minus 1 squared. So we still have linear factors, but they're not distinct because we have x minus 1 times x minus 1. It's the same factor. So we couldn't do a over x minus 1 plus b over x minus 1 because that wouldn't help us out any. So what we have to do is have a over x minus 1 and b over x minus 1 squared. So that's the purpose is finding a and b. So we do the same thing. We cross multiply these to get the numerator. And we multiply we don't multiply the denominators together in this case. We actually, let's go back one step. We don't cross multiply it. This one already has the same denominator as the original term. So we just need to multiply this term by x minus 1 divided by x minus 1. So when you do that, you get a times x minus 1 over x minus 1 squared, and then you have the second term, which you don't have to do anything to, b over x minus 1 squared. So now we have the denominators equal to each other, so we set the numerators equal to each other. Now, when we had distinct linear factors, we chose x to be whatever made the two factors go to 0. Well, in this case, we don't have a second factor. So we're going to still choose x equals 1 to get rid of a to solve for b. And we're going to choose x equals 0. Now, we could choose x equals anything. And the only reason we choose 0 because this goes to 0. Otherwise, it doesn't really matter. We'll get the same answer no matter what is the second value of x we choose. So it's simpler in that case. Second choice is always 0. The problem is we have to solve for b using this, and then knowing b, we have to solve for a. So it's a little bit more tricky, a little trickier. So we're going to do this one first, just like we did before. So if we let x equals 1, this term will go to 0. So a drops out, and we just solve for b directly. So that's what happens here. So put in x equals 1. 2 times 1 minus 3 is equal to a times 1 minus 1, which is 0, plus b. So that goes to 0. So you get 2 minus 3 is negative 1. B equals negative 1. So that's the coefficient b. Here we let x equal 0, so you get 2 times 0 minus 3 plus a times 0 minus 1 plus b. So we have to use this. We have to substitute that into here. So 2 times 0 is 0, minus 3 equals a times negative 1, negative a. And b from the previous part is negative 1. So we can take the negative 1 to the other side, becomes positive 1. Negative 3 plus 1 is negative 2. So we get negative 2 equals negative a, or a equals 2. So those are our coefficients. And so our original fraction here becomes a, which is 2. Just noticed I did that wrong, I guess. Yeah, guess nobody caught me this morning. Okay, so this is actually positive 2 over x minus 1, and then you've got b, which was negative 1, so you get negative 1 over x minus 1 squared. Okay, so let's fix that there. So if we want to integrate the original rational function, it's equivalent to integrating these two separately. So we can factor out the 2. We're left with 1 over x minus 1 dx. And we have negative 1 from here times 1 over x minus 1 squared dx. So this is the same as yesterday. The integral of 1 over x minus 1 dx is the natural log of the absolute value of x minus 1 multiplied by 2. So again, fix the negative sign. So you get 2 times the natural log of x minus 1. The integral of 1 over x minus 1 squared dx. Okay, this is on the next page. So here it's just u substitution. You let u be the denominator, not the denominator, but the term in these parentheses. So u is x minus 1, so du is just dx. Derivative of x is 1 times dx. So you make those substitutions into here, so you get this becomes u, this becomes du. So you get 1 over u squared du. Move that to the numerator, becomes a negative 2. Integrate, add 1 to the exponent, divide by the new exponent. Move this to the denominator, so u to the minus 1 is 1 over u. And then you plug u back in, so you get negative 1 over x minus 1 plus c. So that comes over here. So we get a negative from here and a negative from there. Those cancel out. So it becomes positive. Fix that. And that's your answer. So when you have repeat linear factors, you'll have a natural log term and you'll have a reciprocal term. So there's your homework. This is distinct linear factors and repeat linear factors. So probably 2 of them are distinct. One's probably repeat. It's more likely to get repeat linear factors. Okay, now before we move on to the quadratic factors, we're going to look at what happens if you have an improper fraction. So it's an improper fraction because the order of the numerator, the highest exponent, 3, is greater than the denominator. So we're going to use long division to rewrite this as a linear term plus a remainder. The remainder will be something over x squared minus 2 minus 8. So here it is. So you say, okay, what do I need to multiply x squared by to get 2x cubed? The answer is 2x. So that is how you choose the number up here with a term, and then you multiply out all three terms. 2x times x squared is 2x cubed. 2x times negative 2x is negative 4x squared. 2x times negative 8 is negative 16x. Then what we do is we subtract these three terms from this original numerator. So this goes to 0. That's because we chose it to happen. Here we have negative 4, and you have a negative times a negative is a positive, so it's negative 4 plus 4, which is 0. So that goes to 0. Then you have negative 15, and then you've got negative times a negative, so it's negative 15 plus 16, which is plus 1x. And then you bring the 5 down. Now because this went to 0, it's just going to be 2x plus 0, and then the remaining part of it is going to be x plus 5 divided by x squared minus 2x minus 8. So this original improper fraction is kind of like almost like a mixed number in some ways. You got the whole part and then the fraction part. So the whole part is that. If this was not 0, then I would include whatever that constant is. Now the numerator is smaller, lower order than the denominator, so it's not an improper fraction anymore. So this part is always easy. The parts you get here are just going to be simple polynomial integration. So the integral of 2x is 2 times x squared over 2. Add 1 to the exponent, divided by the new exponent. And then the second part, we're going to have we have to use partial fractions to break that into two parts. The result is that, but let's go to the next page and show you how you do that. So I promised that we were going to do it again. So here we go. So if we factor the denominator, x squared minus 2x minus 8 is x plus 2 times x minus 4. We now further want to break that into two fractions that involve the two linear terms. So we have a over x plus 2 plus b over x minus 4. And again, it doesn't matter which one you have first. You're going to get the right answer. If you switch these, then a and b will be switched, so they'll be in the right place. So cross multiply the denominators together. You get that. So a times that plus b times that gives you the numerator, and this times that gives you the denominator. What that does now is we have the same denominator, so we can set the numerators equal to each other. And again, we're going to choose x to be such that this goes to 0 and the x such that this goes to 0. So to make x minus 4 equals 0, x is equal to 4, and to make x plus 2 equals 0, you make x equals negative 2. So those are the two values of x we're going to choose and plug in to solve for a and b. So for x equals 4, just this choice, plug them in there. Different than last time, we have x plus 5 over here, so we're going to have to plug in x equals 4 here and x equals 4 there. So we'll get 4 plus 5 instead of x plus 5 is equal to a times 4 minus 4, which is 0, plus b times 4 plus 2. So 4, 4, 4. So that goes to 0. 5 plus 4 is 9. 4 plus 2 is 6. So let's divide by 6. You get 9/6. I did that wrong too. Boy, they were not awake this morning. 0.96 3/2. Maybe I wasn't awake. Okay, so that's B. Then you do x equals -2. So -2, -2, -2, -2, -2, -2. That makes this term go to 0. So we got -2 plus 5 is 3. -2 minus 4 is -6. 3 divided by -6 is -1/2. So A is -1/2. So this would become 3/2 instead of 2/3. Okay. So A is -1/2. A goes with x plus 2. B is 3/2. 3/2 goes with x minus 4. So now we can go back here. Again, we can correct that. 3/2. It should be 3/2. Okay, so when you integrate these, because they're distinct linear factors, we just take the coefficient -1/2 and then multiply by the natural log of the absolute value of this thing. And then we have 3/2 times the natural log of the absolute value of x minus 4 plus c. And that's your final answer. Okay, so the next thing is a distinct linear factor and a quadratic factor. Now, I'm thinking about it, up to this point we just had a second order polynomial in the denominator because we got a linear term times a linear term. Same here with repeat linear factors. It's the second order, and the first one is second order. So they're all just second order. Now, when you start to do quadratic factors and a linear factor, then you're going to end up, if you multiply these out, you're going to end up with a third order denominator. So the difference is, well, the similarities is the linear part has just constant in the numerator a divided by x plus 1, so that's nothing new. But when you have a quadratic factor, you have bx plus c. Now, right now we're starting off with just a quadratic term and a constant term. But later on we'll put in a linear term, and you would still have bx plus c. So as long as the highest order term is squared. The other thing is that this stays quadratic because you can't factor this. There's no real factors. There's no real zeros. So this, if you have a third order equation, if you multiply these out, and you get one real zero and two complex zeros, then the complex part you just leave as a quadratic term. Okay, so again, we can cross multiply here because we just have two terms. So you take a times this plus this times that, or that times that, doesn't matter, divided by these two multiplied together. So we're at this point where the denominators are the same, so we can set the numerators equal to each other. Now, I don't have a quadratic term over here, but I can put one in and just make the coefficient 0, and you'll see why that's important. So, in contrast to what we did with distinct linear factors, here we can't set x equal to some value and make things disappear completely. I mean, I guess I could make x equal -1, and that would make that go to 0. So we could get a, but you can't get b and c by doing that. I've never done this before, but I should be able to do that. So if I did let x equal -1 to make that term go to 0, I'd have 0 times -1 squared plus 3 times negative 1 plus 2 is equal to a times negative 1 quantity squared plus 4, and then plus negative 1 plus 1 times this term, because that's 0, it doesn't really matter what that second term is. So that's going to go to 0. So you're going to end up with negative 3 plus 2 is equal to 5a. Negative 1 squared is positive 1. Positive 1 plus 4 is positive 5. And then we have negative 3 plus 2 is negative 1. So you get a is equal to negative 1/5. Okay. We'll come back and see that that's correct, but we don't need to do it in this case. So what we do is we multiply all these terms out. So you'll take a times x squared, a times 4, then you use FOIL, so you get x times bx, which is bx squared. Next one would be 1 times c, which is cx. Nope, sorry, x times c, cx. So that's the outer. The inner is 1 times bx. And then you have 1 times c, which is c. And then you group the terms that have x squared in front of them, the terms that have x in front of them, and the ones that don't have either x squared or x, just the constant terms together. So we group them in that way. So we've got a and plus b. A plus b times x squared, those are those two terms. Let's just mark them out once we've taken care of them. Have these two terms, so it's c plus b times x, factoring out these terms. And then we've got 4a plus c left over. So if we now set the coefficients in front of each term on the left-hand side and the right-hand side equal to each other, then we'll end up with 3 equations and 3 unknowns. So on the left-hand side, the coefficient here is 0. On the right-hand side, it's a plus b. So you get 0 is equal to a plus b. The second, you got 3 is equal to c plus b. 3 is equal to c plus b. And 2 is equal to 4a plus c. 2 is equal to 4a plus c. So these are our 3 equations. This one right here, this one right there. So, you know, there are multiple ways of solving simultaneous linear equations. In this case, what I can do is I can solve this equation for a. So if I move this to the other side, it becomes negative b. So you get a equals negative b here. I can move b over here, so that becomes negative b. So you get c is equal to 3 minus b. And then you substitute those into the third equation. So that third equation is originally a function of a and b, a and c, but by solving for a and c here and plugging it in, the third equation becomes just a function of b. So you get 2 is equal to 4 times a, but a is negative b, plus c, c is 3 minus b. So negative b times 4 is negative 4b, 3 minus b. Combine like terms, negative 4b minus 1 is negative 5b. 3 goes to the other side, becomes negative 3. Negative 3 plus 2 is negative 1. Divide both sides by negative 5. Negatives cancel out. You get b is equal to 1/5. And then what you can do is you can go back and use these equations to find a and b. So a is negative b, so a would be negative 1/5, which we already knew from this previous step. So that's where we get a. So b is 1/5 from this right here. A is equal to negative b from here, and c is equal to 3 minus b. So 3 minus 1/5, this is 15/5 minus 1/5 is 14/5. So our original equation that had a distinct linear factor and a distinct quadratic factor now becomes a, which is negative 1/5, so you get negative 1 over 5x plus 1, plus, and what I've done here is, notice b is 1/5, and c is 14/5. So I factored out a fifth. That leaves just x. So instead of b being a fifth, you just have 1 here, and then c is 14/5. So that's, if I want to integrate my original expression, it's the same as integrating this expression. So let's do that. So the integral of 3x plus 2 over x plus 1 times x squared plus 4 dx is this. So you factor out the negative 1/5. That leaves 1 over x plus 1 dx. Then we take this part, x over x squared plus 4, so you get 1/5 x over x squared plus 4 dx, so that's the first part, and then you have the second part, so you factor out the 14, so you get 14/5 divided by x squared plus 4. This one's easy, natural log of the absolute value of x plus 1. The second two, you have this, which you would use u substitution, where you'd let the entire denominator be x squared plus 4. So that's u, so we're going to get 1 over u. If you take the derivative of x squared, you get 2x multiplied by dx. So du is 2x dx, but in the original expression I have x dx, so I divide both sides by 2. So x dx equals du over 2. So that's for this one. So this is going to involve the natural log of this thing. And the last one is an inverse trig function type thing, where you're going to have the arctangent 1 over u squared plus a squared. So u in this case is just x. That's u squared. A is 2. 2 squared is 4. So that's u squared plus a squared. And if you take the derivative of u, derivative of this, you get du. Derivative of x is 1 times dx. Gives you the du part. So here we have 1/5. 1 over x squared plus 4 is 1 over u. X dx is du over 2. Here, x squared is u squared. 4 is a squared. So you can look both of those up in your integral tables. The integral of 1 over u du is the natural log of the absolute value of u. 1/5 times a half is a tenth. The integral of 1 over u squared plus a squared du is 1 over a arctangent of a over u. So now we can plug it back in. U for this part, for the first integral, is x squared plus 4. So we get the natural log of the absolute value of x squared plus 4. A in the second part is 2. So here's 2 and here's 2. And then u is x. And then a final answer here. So the integral of 3x plus 2 over x plus 1, x squared plus 4 dx is the integral of this, which is negative 1/5 times the natural log of the absolute value of x plus 1. The second integral we just did, it's 1/10 natural log of x squared plus 4. Here you get 14 over 10, which we could simplify to 7 over 5 if 1, 2, arctangent of x over 2 plus c. So, let's just show this 7 over 2. And that's it. So I'm going to show you the homework assignment for this. We're going to do repeat quadratic factors. But before we do that, we're going to do a more complicated problem, but we'll do that next time. So these are the problems that involve a distinct linear factor and a quadratic factor, and as well as a repeat quadratic factor. So there you go. It's shorter than the class because you can pause this recording if I went too fast.